Let's consider the following polynomial inequality. We would like to solve for all values of x for which 2x cubed plus x squared plus 6 is greater than or equal to 13x. The best way to approach a problem like this is to get 0 on one of the sides. So if I subtract 13x from both sides, we can see that this turns into 2x cubed plus x squared minus 13x plus 6 is greater than or equal to 0. Now the next thing I want to do here is I want to treat this like a polynomial function, let's say p of x, and I'm going to factor this polynomial function. So to factor it, of course, we could use synthetic division, for example. Now I'm going to speed up the process here a little bit, but it turns out that 2 is one of the zeros, and so I'll go ahead and go through and just show that here. And then, of course, we have 2x squared plus 5x minus 3. And if we factor that, we get the following. And so the complete factorization of p of x is x minus 2 times 2x minus 1 times x plus 3. And again, we're wanting to know when is this greater than or equal to 0. So I'm going to show you a very simple way to solve these inequalities, and that is to treat this like a polynomial function and sketch the graph. So we know that the x-intercepts are at 2, 1/2, and -3. And so you can see here we have an x-intercept at 2, -1/2, and, positive 1/2, and -3. And then we know because of the end behavior, etc., for this function, that the graph of this polynomial must look something like this. And it doesn't have to be a perfect graph, but we know the overall behavior is something like this. So when we say we're solving for when the polynomial is greater than or equal to 0, remember, p of x is the y value. And when the y value is greater than 0, that means it's above the x-axis. So what are the portions of the polynomial that are above the x-axis? Well, they are these portions right here, this portion, and also this portion. Now, of course, we don't have to have a graph to see this. What you can do instead is you can make a number line and you can test each of the intervals in between the x-intercepts. And we'll talk about that in just a minute down here. But if you look at the graph, we can see that the values of x for which the polynomial is above the x-axis is going to be the values in between -3 and positive 1/2. So these values of x here. And also the values of x that are greater than 2. Now, because we have greater than or equal to here, we're going to describe our final solution as all of these x values or all of these x values. And of course, in interval notation, that would just look like this. So here is our solution. Now what I want to do is talk about a different way to approach it without graphing. So another way to approach this is to simply recognize that this polynomial is going to equal 0 when x equals 2, when x equals 1/2, and when x equals -3. So what I can do is I can draw a number line, and I can put these values on that number line. And then I just need to test to see if the polynomial is going to be greater than 0 in between the values at which it's equal to 0. So one way to do this is we can simply pick test numbers. So I can test, say, x equals -10 here, x equals 0 here, and x equals 1 here. And let's say x equals 5 over here. And then we could just plug those in and observe whether it's positive or negative. But there is another way to do it. If we consider each of these factors independently, we can talk about the sign of each of the factors. So for example, the first factor here, x minus 2, when is it positive and when is it negative? Well, we know that x minus 2 equals 0 at 2. If you plug in any number bigger than 2, it's going to be positive. But if you plug in any number here less than 2, it's going to be negative. So the factor x minus 2 is going to be negative for all three of these intervals, which is this one, and this one, and it will be positive for this interval. And then we do the same thing for the other factors. So the next factor is 2x minus 1. We know that 2x minus 1 equals 0 at 1/2. If you plug in a number greater than 1/2, you will get a positive number. And if you plug in a number less than 1/2, you will get a negative number. Likewise, x plus 3 is equal to 0 at -3. If you plug in a number larger than -3, you will get a positive number. And if you plug in a number less than -3, you will get a negative number. And so now when we're on, say, this interval right here, what we have from each of these three factors is a negative number times a negative number times a negative number. And the product of three negative numbers is a negative number. So we know that the polynomial will be negative on this interval. On the next interval, in between -3 and positive 1/2, we can see that it's going to be positive because what we have there is a negative number times a negative number times a positive number. And the product of one positive and two negatives is positive. So it will be positive on this interval. And then for the next interval, in between 1/2 and 2, you can see that we have a negative times a positive, which ultimately is a negative. And then finally, for the interval where x is greater than 2, you can see we have three positive numbers, and the product of three positive numbers is a positive number. And so what's our solution? Well, remember, we want p of x, which is this polynomial, to be greater than or equal to 0. Greater than or equal to 0 means non-negative. So which intervals is it going to be non-negative? Well, that's going to be the intervals where the polynomial is positive, right? And so it's going to be all the values from -3 up to positive 1/2, union all the values from 2 to infinity. So this is another way to do it. And to be honest with you, this is the way we normally solve these kinds of inequalities. We don't normally graph the polynomial function. Instead, we do this, which is a little bit faster. So the steps for solving polynomial inequalities, you can read through these on your own, but basically you want to move all terms to one side, so you'll have 0 on the other side. Then you want to factor the polynomial, and we're only interested in factors involving the real zeros. We don't care too much about complex zeros because complex numbers don't show up on the real number line. Next, you find the intervals. So you draw a number line and you define the intervals at which you need to investigate. And then you make a table or a diagram to determine where the inequality is true. And finally, you solve it by putting it all together. Let's take a look at another example. So here I want to solve the following polynomial inequality. First thing I'm going to do is move these terms over to the other side by subtracting. So we have 3x to the fourth minus 2x cubed minus x squared minus 12x minus 4 is less than 0. So notice that I want to put all these terms in descending order when I move these over to the other side. Now I need to factor this polynomial. Now I'm going to skip the work on this, but again, you could use synthetic division to factor this. But when you factor it, you will find that you get 3x plus 1 multiplied by x minus 2 multiplied by x squared plus x plus 2. And we want this to be less than 0. So now, of course, one way to do this, if you view this as a polynomial p of x, is you could graph the polynomial p of x, and you can see over here I have a graph of that polynomial. Notice that there are only two x-intercepts. You have one x-intercept at x equals 2. That comes from this factor. You have the other x-intercept at x equals -1/3. And that comes from this factor. And the reason there are no other x-intercepts is because the zeros for this factor are complex numbers. So we will ignore this factor. So now if I look at the graph, I want the portion of the polynomial that is less than 0. So in this case, that means we want the portion that is below the x-axis. And that portion is this piece of the graph right here. And so just using that alone, we can see that the solution is all the points from negative 1/3 to positive 2. And so that's one way to get the answer. Now, of course, we want to be able to do this without graphing, because when you don't have the benefit of having the graph provided for you, it's going to be a little bit harder to find the solution by graphing, right? Because you're going to have to actually graph the polynomial. So let's talk about the way to do this using a table. So just like in the previous problem, we're going to use a table where we only list the real zeros. And again, those zeros are negative 1/3 and positive 2. And then we're going to look at the sign of each one of these factors on those intervals. So the sign of x minus 2 is positive when x is bigger than 2. It's negative when x is less than 2. The sign of 3x plus 1 is positive when x is greater than 1/3, negative 1/3, excuse me. And it's negative when x is less than negative 1/3. And the sign of x squared plus x plus 2, believe it or not, is positive on all three intervals. So the reason for this is because this has no real zeros, which means that it's either always going to be positive or it's always going to be negative. In this case, if you just plug in a sample value for x, you will find that it is positive no matter what. So now, what is the sign of the product of these factors? Well, again, we only care about when the sign is negative because we want the polynomial to be less than 0. And that is negative on this interval right here, in between negative 1/3 and positive 2, which is consistent with the answer that we got right here. Now, in this case, we do not include the endpoints because we do not have inclusion here. Solving a rational inequality is very similar to solving a polynomial inequality. We're going to move all the terms to one side, and then we're going to factor the numerator and the denominator, and then we're going to find the intervals and then solve using a table or a diagram. Let's go ahead and take a look at an example of solving a rational inequality. Now, my description here previously probably made it sound just as easy as solving a polynomial inequality. It is not quite as easy because we are dealing with fractions. So in the first step, when I want to get 0 over here on this side, I have to subtract 1 from both sides. But when I subtract 1, we're going to get this, right? Because when you subtract 1, you can't actually subtract it from this fraction here. So the next step is we need to combine these. And to do this, we need to have a common denominator. So what I'm going to do here with this 1 is I'm going to re-express it as x squared minus 2x minus 3 over x squared minus 2x minus 3. Okay, so basically I'm just using the denominator that is common with this denominator. And since we had the number 1, the numerator is the same as the denominator, right? So now I can subtract these. And so when I subtract, the denominator is going to be the same. The numerator is going to be 1 minus 2x, and then we have to subtract each one of these things. So it'll be minus x squared plus 2x plus 3. And we want that to be greater than or equal to 0. Now in the next step, what I'm going to do here is combine like terms. So in the numerator, we have negative x squared. And then we have a negative 2x and a positive 2x. Those actually cancel out quite nicely. And all that's left is 1 plus 3, which is positive 4. And the denominator, we have the same thing. And we want this to be greater than or equal to 0. Okay, so now we're going to factor. Now, when we factor here, it's a little bit strange because we have negative x squared plus 4. So what you can do here is you can write that as 4 minus x squared. This is what I would recommend doing. And then 4 minus x squared factors using the difference of two squares into 2 minus x and 2 plus x. And then the denominator factors pretty easily. But in the end, here is the factored form where notice now we have 0 on one side and we have a numerator and denominator that is factored on the other side. So now if you were to graph the rational function r of x equals 2 minus x, 2 plus x over x minus 3 and x plus 1, that graph would look like this down here. This graph that you see down here. And of course, there are some asymptotes in here, right? But what we're looking at is solving this inequality. So we want to know when is the rational function greater than or equal to 0. And of course, that means above the x-axis. So it is above right here, and it is above right here. It is only above in 2 spots, 2 intervals. And of course, there is an asymptote right here, and there is an asymptote right here, and this is at 3, and this one here is at negative 1/2, right? Sorry, negative 1. Negative 1. I don't know why I said negative 1/2. There we go. Okay, so what's the solution? Well, the solution is, where is it above the x-axis? It's above between this value, which is negative 2, and this value, which is negative 1. So we're going to go negative 2 to negative 1. Now we do have equal to here, so we want to do this. It's also above right here, which is from 2 to 3. Okay? But this answer is not completely correct. And let's talk about why. No matter what happens in this problem, if you look at your original denominator, which is this denominator right here, which is this denominator in factored form, we know no matter what happens, x can never be equal to 3 and it can never be equal to negative 1. So even though we want to include negative 1 and we want to include 3 here, we cannot do that. So we have to modify this answer just a little bit so that we make sure that we do not include values that we cannot include. And this is our final solution there. Now, of course, we could also do this using the signs of each of the factors. So what you could do is make a table like we have here with all 4 of these factors, with all 4 of the zeros listed, and then you can just list where each of those factors are positive and negative. Now, one little tricky thing here is with the factor 2 minus x, we know that it's equal to 0 at 2, but it's actually going to be negative when x is greater than 2, and it's going to be positive when x is less than 2, right? And then the other factors here we list, and then we're looking for where it is greater than 0. So in the end, we're looking for where the result is positive, and that is between these 2 values of x and these 2 values of x. And you can see that's consistent with what we have down here. So we'll go ahead and solve one more rational inequality. This one is quite a bit easier in some regard because you'll notice that we already have 0 on the right-hand side. So all I need to do here is factor each of these polynomials. So we have x minus 3 times x minus 1 for the numerator, and in the denominator we have x minus 5 times x plus 1. And again, we want to know when is this greater than or equal to 0. So of course, one way to do it would be to simply graph this rational function. And here is the graph of that rational function. And again, we are looking for all the values of this function that are positive. So that means above the x-axis. So you can see the graph is above the x-axis right here. And also right here. And there's a little piece that is above right here. It's very hard to see, but it does come above the x-axis right there. So according to the graph, we would have all the values of x from negative infinity up to this value, all the values of x between these 2 values, and all the values of x greater than this value here. All right, so basically if we list all the zeros of these factors, you get the numbers -1, 1, 3, and 5. And so that means we have an asymptote right here at -1. And we have an asymptote over here at +5. And then we know that this number is +1 and this number is +3. So now using those numbers, we can see the solution is from -infinity up to -1. Union, we want all the numbers in between 1 and 3. Union, all the numbers from 5 to infinity. And we do want equal, right? So we want to use brackets, but again, we cannot include 5 or -1 because that makes the denominator 0. So we cannot include -1, we cannot include 5, but we are going to include +1 and we are going to include +3. And so this would be the solution according to the graph. Now, of course, you could also do that using a number line and figuring out the signs of all of your factors there. And again, we're looking for where the result is positive in the end. So that is going to be all of these values of x, these values of x, and these values of x. And that is consistent with what we have down below. And that concludes this video lesson.